Hello and welcome to the latest student tutorial. This one focuses on the effective use of the Nspire calculator for further maths in Victoria, graphs and relations module. My name is David Tynan. So today we'll be looking at a number of problems that come from the graphs and relations module. And all of these are based on recent exam questions, but are variations on those questions. So we start by looking at a variation problem. Particularly, they discovered that there was a relationship between the average speed for a journey for Jemima travelling to work and the time in hours that it takes her to reach it. And you can see the equation that goes there with the constant of proportionality, K. And then we have two bits of data. On the worst day, Jemima drives to work, it takes 2.5 hours, an average speed of 32 kilometres an hour, and on the best days, the drive to work takes 1 hour and 15 minutes at an average speed of 64 kilometres. So the questions find the value of K. It's not too hard using one of those bits of information. Then draw a graph between the average speed and 1 over the time, which should be a straight line, and interpret the gradient. And then draw a graph of average speed versus time, and then answer a question which is interpreting that in the context of a change in the average speed. So let's now move to the calculator window. And so the first value that we have is the 32 kilometres an hour as the average speed, and that will take her 2.5 hours. And so if you just type that in, the calculator will make a little change to that, but it's essentially an easy solve. You could just do 32 times 2.5 to get 80. In this case, I just divided by 0.4. and the result is still the same. So that's really the first question sorted. For the next bit, for B, you have to draw a graph of average speed versus 1 over time. So one thing that you could do is to just put those two values into a spreadsheet on your calculator. Just add a spreadsheet page and you'll see the two known values in there for that. So that's the 1.25 hours at a speed of 64 kilometres an hour, and the previous value that we mentioned. Then you can create a formula. I've called it rec for reciprocal, the reciprocal of the x value, because that's what you're being asked to do, and that's in the next row is where you can put in column formulas. And I've put in a column formula which is that the values in that column should be 1 divided by the x val. And you'll notice the decimal point here. That decimal point is there just to force it, if you're not in approximate mode, to force it to give decimal answers rather than fractional answers. Okay. In the related exam question, you had to graph this, that is the average speed versus 1 over time, and complete that on the exam paper. So what's happened here is, by graphing the y value against not the x value, but the reciprocal of the x value, you end up with a straight line. We've just got 2 points, and this is just fitting a regression line that passes through those points, and it says 0 plus 80x. So it's just 80x, or unsurprisingly telling us that the k value is 80. Okay, moving on to part C, where we get to see the actual relationship of y versus x, or if you like, average speed against the time taken. And you'll notice that the way I've defined it is to say the graph is y equals 80 over x, but I've put in a condition here, that is that I'm only really interested for values of X, or if you like, values of the time between 1 and 3 hours, just based on the data that's there. I wanted to mention a couple of things here because they're useful skills when you're graphing. The grid is really useful for this. So I'll just show a couple of things just by going back to the standard viewing window. So if I go to Zoom standard, if you were to do this, you'll find that the graph doesn't show very well. And so what I often do and ask my students in further maths and maths methods to do is to go to the window, and in the window settings, think about the X values that you're interested in, or if you like, the times. And I'm just going to put in 1 to 3, and I'm going to put in, say, a quarter or 0.25 as the marks on the X-axis. So that sort of suits my purpose, and then I can press OK. The graph's still not there, but then there's a nice setting here for zooming, menu, zoom, zoom fit, and that will immediately make the graph come into view. Now, I did a couple of other things which I probably should mention. In order to get a nice view of it, I've changed some of these boundaries. So that bit's okay with the quarter. I'm just going to round this off and make it, say, 20 to 90. And I'm going to put in here just markings of 10. Okay, so now we've got a nice view of the graph. One other setting which is on at the moment but isn't always on, if I'm to highlight near the axis, you can control. These numbers are here. That's a setting in the attributes for the axes. So it's possible for you to, I'll just show the step. And attributes. And this is not often used, but these are the attributes for the axes. Down here, the standard viewing thing is just to show the ticks for the ends and the grid spacing. But if I change to this, if you haven't got too many splits in the X or the Y, then it will be able to show it in the more standard way of showing every grid spacing. And that's what I've elected to do. So just a quick trace of seeing how the graph behaves. Remember, if I was to type the number 1.25, it should show me that that's associated with an average speed of 64 kilometres an hour. Okay. The last part of this question is just asking if she could increase her average speed from 50 kilometres an hour to 100 kilometres an hour, how much time would that save? So just with trace, I'm able to type in numbers for the time, but I can't type in numbers for the average speed in this context. And so it's not as easy just to trace or jump to the spot which is exactly 50 kilometres an hour, associated with exactly 50 kilometres an hour, and even 100's not showing. So instead of viewing it that way, it's possible just to just type in that you want to know what is the time that it would take the journey using the given formula if you wanted to have an average speed of 100. And this little bit at the end here is the vertical symbol. It's just a condition you're saying, solve it in the circumstance where the average speed is 100. And that command, if you can't recall, is just in control equals. So I'll just do it down here. So if I do control equals, you get a pop-up palette, and it's that symbol that you want. Okay, so then I do that for 100 kilometres an hour and 50 kilometres an hour and look at the difference in the time and just get those two answers and subtract them. And because that's in hours, I just multiply by 60 to tell me that the answer is that it will save 48 minutes if I'm to increase my average speed from 50 to 100. Okay, so that's problem 1. So now let's look at problem 2. So problem 2 is a hybrid function, and it's about two people walking. Jerry and Massimo, and their house is 700 metres in a direct line. At a particular time, 3 p.m, Jerry's at the house and heads to the station from the house. And at the same time, Massimo is heading from the station back to the house. So we start with Jerry's rule, which is a hybrid function with 3 parts. And we'll define that and work with that, and then we'll work on Massimo's. So we'll refer back to the question as we work through the problem on the calculator. So back to this, and now we're on to problem 2. So you'll notice that I've defined the function. If you're not familiar with this notation, you probably are, but if you're not, this is saying this is Jerry's walking. Remember that Jerry's equation, it's her distance in metres from the house after t minutes. And Massimo's equation is also the distance in metres from the house. Okay, so I think you will all know, if you're doing this module, that in the templates key you can access the template for entering a hybrid function based on the number of pieces you've got. So just to save time, I've done that already, but it's come straight from the problem. So G of t, so that just means Jerry's distance from the house at time t. And we'll see later there's a benefit in typing it like that. So that's not a surprise. And then we'll go down to Massimo's. That's his distance from the house at time t. And I put in the restriction that t is just a number that's greater than or equal to 0. Okay, then question A is able to be easily answered because you've defined the two functions as saying when do they have the same distance from the house? They're coming from different directions, but there'll be a point at which their locations are the same in that 700 metre line, if you like. So solving that, you'll find that you get the answer 4.4 minutes. And you could just subtract 4 and multiply by 60, but I've shown here that you can use the DMS, the degrees, minutes, seconds function, just to convert 4.4 into 4 minutes and 24 seconds. So that is the end of part B. And then the next question is to say, how far has Massimo, sorry, that's part A. So part B is how far has Massimo travelled when their paths cross? Well, if you just substitute in that time of 4.4 minutes into Massimo's equation, that gives you the answer 392. But remember, 392 is Massimo's distance from the house. That's he's coming from the station. So remember that you, in order to answer that correctly, you would have to subtract the 392 from the 700 metres of the total distance in order to get the answer of 308 metres. So he's walked 308 metres. And that was a question that was a lot of students didn't get because of the subtleness of the way that question's worded. Okay, so that's part B. So then the next question is, what time does Jerry arrive at the station? And we expect it to be after 9 minutes, because if you look back at the rule, that's sort of the way that you expect that, but it's worth just checking. If you put 9 into this third piece of the hybrid rule and check, so 960 is a 540 plus 160 is indeed 700, but I've just checked by putting G of 9, which is saying how far is Jerry from the house after 9 minutes, and she is indeed at the station. Okay, and then the final question is, so what speed should Massimo walk so that he arrives at the station at the same time as Jerry arrives at the house? So he's just got to do 700 metres in 9 minutes, which gives you, that's the number of metres a minute. And remember, the question asks in kilometres per hour. So if I multiply that by 60, that tells me how many metres he would do in an hour. And then if I divide that by 1,000, I'll see the answer is approximately 4.7 kilometres per hour. So that's what he needs to walk at. Okay. Because we've defined the rules up here, we're able to graph them as well. And I'll just explain here. You'll notice we've said G of T here and M of T. So it'd be nice if we could just graph G of T and M of T. A restriction in the calculator is that when you're doing graphing, and I'll just double click here, can you see that it doesn't say G of T, it says G of X? And that's because the calculator, when it's doing function graphing, is expecting the independent variable to be the letter X. And so we're still using G for Jerry, but we're using X to represent time. So I've just typed in G of X and it's graphed it quite happily. So you can see the 3 branches of the hybrid function. And you can see Massimo's walking style. And he, unaltered, if he is to walk at the rate that he walked, it was going to take him 10 minutes to get home. Okay, so with all of these problems, some form of visualization is helpful, but it's good to know that you can work with it algebraically even without having it visually represented. Okay, so that's the end of problem 2. And now we'll move to problem 3. So this was a question that was not done well according to the examiners. And this is a question that's based on the same thing. And we're just trying a different method. So the graph on the right is at 212. And what they're asking is, of those 5 options, is there another graph of those, one of those, which represents a relationship in a similar way? Please notice that they've used X here, X squared, X cubed, and X cubed here. So we need a way of checking those points, given that it's graphing not necessarily Y versus X, but Y versus either X squared or X cubed. So let's see a way to attack those problems. That's problem number 3. Okay, so in this I've used a notes page. You don't have to use a notes page, but it's a nice way to represent the problem all at the same time. So if you can remember, or you want to look back at, or you printed out the graphs themselves, what we're going to do is test each of the rules and see whether indeed the point x is 2 does come up as y equals 12. Now, recall the first one. Now, I've defined this function. So this is a maths box in a notes page. If you're not sure how to do this, then you can download the file and have a look, or you can watch one of the other webinars that focused on producing notes pages. There is an up-and-coming one done by Craig Brown. He's doing a webinar on doing notes for the modules. So maybe that one would be worth watching if you want to know how to create these things. Anyway, so I've defined a function y, which takes x values, and that's the rule that they gave in the problem, k times x to the n. And we're just going to test these other values. So we're using another maths box here to say, well, is y2 equal to 12? Let's see what y of 2 is. So what's y of 2 in the case when the k value is 6 over 1? That is, the graph shows a single point at 1, 6. And so doing the y1 value over the x1 value will give us the k. And the n value in that is 1. That is, it's a linear graph. It's just the graph of y equals kx. So if you do that substitution, it tells you that y is indeed 12. However, there's a problem. And the problem is that it's already linear. And so it won't be equivalent to the more curved graph that is showing there. So we can discard A. Using similar strategy, you can discard B, graph B, graph C, which you'll notice in B and C, the n value is 2, that is, it's x squared that y is being graphed against. The point substituted, and no, you don't get 12. You don't get 12. And the part D, the graph is a cubic, and with the values that have been chosen there, it gives the value 48. And so it's only E, which is y against x cubed. And if you use the k value and the n value chosen, you do indeed get 12. And so that's the answer. So again, you don't need to use the notes page, but it is another way of quickly checking your result. And let's finish with problem 4, which is a linear programming problem. And I haven't got time in the half hour to go through all the details, but essentially in the dot points there is people are attending a regional competition and have to hire cars and minibuses. And you'll notice that, so X is the number of cars they use, Y is the number of minibuses, and there are a number of constraints about the number of vehicles, how many cars, how many minibuses, how many can be carried in each car and each bus, so more in the minibus, that is 10, and only 5 in the cars. And then they can't have any more than 60 people at the competition. And then they have an objective function listed there, which is that they get the excellent hiring cost of $30 a car and $40 for the minibus, which seems very cheap, but we suggest that it's subsidised. So the question is, what is the minimum cost that meets those conditions? How many cars and buses is involved and how many can attend? And then we look at some other cases. What if you want to take more than what the answer to question A suggests? You're interested in taking 50 people or you're taking 60 people. Okay, so in the time, let's jump back to problem number 4. So there's a couple of things here. Again, this is a notes page, and the notes page has been split. It doesn't have to be split. It just helps with seeing the key things. So the constraints that I've mentioned there, I've stored as relations. So a relation just lets you write it in terms of X and Y without having saying Y is equal to something. So we've got 4 relations that we've listed there. So this is the thing, the number of car and buses have to add up to 8. The cars must be at least 2. The buses must be at least 3. At least 3. And then this is the condition based on a total of 60 people. And notice the objective functions listed here, as well as a little input template for working out the objective function for any entered value of X and Y. Okay, the box on the left here is for points of intersection. Now, we're talking about inequalities, but in order to find points of intersection, it makes sense to call them equalities or express them as equalities. And so you'll notice that I haven't used inequalities in the rules that I've entered in. I've just used the equivalent or the associated equality equation. Okay, so this is a method for finding the point of intersection, which is here. So I'll just hover over this for a bit. So this is saying to find the point of intersection of relation 1 and relation 3, just do a solve. When does relation 1 equal relation 3? And give me the answer to that, the X and the Y value. So that's what that's for. You'll notice that it does it for all of the 6 possible points of intersection. Okay. On the right panel on the bottom is the objective function evaluated for those intersections. So you recall, if you're doing this in the module, that you're often interested in the not just the coordinates of the vertices of the feasible region, you're also interested in what does that mean for the objective value, whether it's profit or cost or whatever. So this calculation is saying what is the value of 30x plus 40y, the OBJ or objective function, at that point of intersection. And if you scroll down through here, you can see, okay, it looks like relation 2 and 3 will give me the minimum cost of those. Now, you need to be careful with these. Even though there are 6 points of intersection, it's not true that they're all valid as part of the feasible region. And so now I'm going to jump to the graph to make more sense of this. So here's a nice visualization of the feasible region, shaded in grey. And all the constraints have been, the lines associated with those have been marked in, as well as you'll notice the dots that are there, the points clearly marked are there as either in the feasible region. You notice we did 6 points of intersection. These 2 here, the one at 2.6 and the one at 6.3 are not valid. They're outside of the feasible region. But these ones are all feasible, anyone in here, but in course in the context, we're only talking about integer solutions for X and Y. We only have a whole number answer for car and bus. We don't really want to have 1.5 cars. So you'll notice that there's a green function here, which is the objective function, and it just pops up. It's a little bit hard to see, but on the left of the top left of the calculator screen, it says the objective function. And this is a little slider here. So in order to answer the first part of the question, we're sliding this down until we get to the minimum here. So it's a little bit tedious to see it slide through the entire thing, but it becomes clear that the cheapest thing, because of the gradient of the objective function, will happen down at 2.3, and it should give us the value of 180, which is what we saw in the notes page previously. And here we are, okay? So that helps answer part A. However, the problem with that is that that's 2 cars and 3 buses. So that's 2 lots of 5 and 3 lots of 10. So that's only 40 people that can attend. So the following questions ask you to look at 50 cars. So there's 2 options for that. The 0.24, which works. So that's X is 2 and Y is 4. So if we slide back, the 0.24 will tell us that you could use that combination, 2 cars and 4 buses, and that would cost $220. Or you could go a little bit further to the 0.43, 4 cars and 3 buses, and that would be $240 and a little bit more expensive. So this is quite a nice way to visualise what's meant when you're working inside the feasible region and interested in not just the minimum or the maximum, but sometimes you've got some other information that you're interested in. You might want 50 people to take to the conference or 60. And I think the final question is just related to that in the context, if we really wanted to take 60 people, how many would we take? However, our time is up, and so remember that all of the files associated with this and the worksheet and the calculator files will be sent to you, or a link to those files will be sent to you not too long after the webinar has completed. And that's all from me today, because I think the next session you'll go to will be the notes and programming and user-defined function section, I think beginning next Wednesday. Okay, thanks for that.